In this video, we're going to look at the equations we got in our previous video and have a little practice in using these equations. So here's the first example that we're going to deal with here. We have a 30 amp current which is running through a wire with 12 centimeters exposed to a magnetic field of 0.9 teslas at an angle of 60 degrees. What is the magnitude and direction of the magnetic force? Okay, let's start off by looking at the direction. Remember, the right-hand rule says that first you point your right-hand fingers in the direction of the current. So point your fingers up and to the right. Then turn your hand so that you can curl your fingers in the direction of the magnetic field, which is to the right. So you should be able to curl your fingers in that direction. The only way to do that is if your thumb is pointing into the board. And so we get our magnetic field, or excuse me, our magnetic force into the board. And here's just a simple diagram showing the same thing. All right, now let's take a look at the magnitude. Well, you'll recall that the magnetic force is going to equal the product of the current times the length of wire exposed times the strength of the magnetic field times the sine of the angle in between them. So that's easy enough. We have all that information. It's 30 amps times length of wire exposed is 20 centimeters or 12.12 meters. The strength of the magnetic field is 0.90 Tesla times the sine of 60 degrees. Now I'm going to pull out my calculator so I can actually calculate all these. So I'm going to do 30 times 0.12 times 0.9 times the sine of 60. And that gives me a total magnetic force of 2.816 newtons. All right, let's do another example. This time we have a charge. An electric charge of 0.3 microcoulombs has an eastward velocity of 20 meters per second. If it passes through an upward magnetic field of 0.75 teslas, what is the magnetic force on the charge? So this is the situation we have right here. The charge is moving to the east. The magnetic field is oriented upward. Okay, so we want to know the magnetic force. Again, we use the right-hand rule. Right-hand fingers in the direction of your velocity, so they're pointing to the right. Turn your hand so that your fingers can curl up to the direction of your magnetic field B. And the only way to do that is if your thumb is pointed towards you coming out of the page. So your magnetic force is out of the board. All right. So in this case, we're dealing with an electric charge. So we're going to use this form of the equation, that the magnetic force is equal to QVB sine theta. Q is 0.30 times 10 to the minus 6th coulombs times the velocity of 20 meters per second times a magnetic field of 0.75 Tesla. And what's the angle between your velocity and your magnetic field? Well, in this case, it's a right angle. So we're going to multiply that by sine of 90 degrees, which, by the way, is just 1. All right, so plug all that into your calculator. What do we get? We get a charge, the charge is 0.3 times 10 to the minus 6th times a velocity of 20 times a magnetic field of 0.75. That means I have a force of 4.5 times 10 to the minus 6th newtons, or 4.5 micronewtons. Okay, just to point something out here, we found that the charge of 0.3 microcoulombs is coming out of the page at 4.5 micronewtons. What if it had been a charge of negative, excuse me, let me get my ink color here. What if Q was equal to a negative 0.3 microcoulombs? Well, then the magnetic force would be opposite directions, because putting in a negative in your equation would give you a negative force, meaning it's just the opposite direction. Magnitude, remember magnitude, we don't care about sign, so it would still be 4.5 micronewtons. It would still be the same magnitude, 4.5 micronewtons. But because it's a negative charge, the force would be into the board instead of out of the board.